All right, so in the last part of this problem, we're going to again assume that when the screw falls off, the elevator is accelerating at 2.2 meters per second squared, and at the instant velocity of the elevator was 2.2 meters per second upward, and we're going to say up is positive. But this time we're going to solve the problem from the viewpoint of a person standing in the elevator. And mathematically, this problem will be easy, but there's a little trick to it you need to understand. So, since you're in the elevator, you can call the elevator floor, the location of the elevator floor, y equals 0. And since you're moving with the elevator, the floor never moves. You still want to set the position of the screw equal to position of the floor when it hits the ground, or when it hits the elevator floor. But in this case, this is going to be 0. Okay? So y floor never changes. I just need to write an equation for the position of the screw. So what's the equation for the position of the screw? Well, it starts 3 meters above the ground. And I really should put the meters there. Now, when the screw falls off the elevator ceiling, its speed relative to u is 0. So its initial velocity relative to u is 0. Okay. So when you try to write the equation for motion at constant acceleration, the initial velocity of the screw in that reference frame is 0. The hard part is writing the acceleration of the screw in your frame. Because we need to know the acceleration of the screw relative to the elevator. And then I want to kind of show you a systematic way to determine that. Some of you might figure that out right away, but I want to figure out a systematic way to figure that out. Okay, I want the magnitude of this thing, so I didn't put in arrowheads. It turns out that we can write the acceleration of the screw relative to the ground, that's 9.8 downward, as equal to the acceleration of the screw relative to the elevator plus the acceleration of the elevator relative to the ground. Where did that come from? Well, let's think about this. And it's very hard to give a direct example with accelerations, but let's do the following. Suppose I'm in an open vehicle, like a cart, okay? And the cart is moving to the right with some speed v of the cart relative to the ground. Okay? And I throw a ball in that direction with some velocity v of the ball relative to the cart. So in other words, let's say the cart's going at 30 miles per hour that way, and I throw the ball at 30 miles per hour relative to me. What's the speed of the object going to be? 30 plus 30 is 60. Okay? And so that's going to be the velocity of the ball relative to the ground. Of course, this is in reality, I mean, in general, this is a vector equation. If you take, and those of you who know calculus, if you take the derivative of this, you get accelerations. And this has the same form as that. And granted, I only did this in one dimension, but this is true in 2 or 3 dimensions. So this equation is true in 2 and 3 dimensions. So I want to know the acceleration of the screw relative to the elevator. So I'm not going to put arrowheads over it because it's a one-dimensional problem. That's going to be equal to the acceleration of the screw relative to the ground minus the acceleration of the elevator relative to the ground. Well, the screw is falling downward at minus 9.8 meters per second squared. And the elevator is moving upward at 2.2 meters per second squared. So when you combine these, the acceleration of the screw relative to the elevator is minus 12 meters, 12.0 meters per second squared. So that's the acceleration of this guy. Okay, so let's put that in. And we're going to set this equal to 0. So let's put the minus 12 in. So I'll erase the board. I don't have a lot of space. So I'm going to have 3 meters minus 1/2 times 12 meters, 12.0 meters per second squared, t squared equals 0. 1/2 of 12 is 6. I'm going to move this to the other side. And I have the same equation as I had before. So t is going to be 0.71 seconds, as we saw before.